The words work and power are words we tend to use fairly often, but may not know the actual definition that we use in physics. If I were to ask you to move that pile of dirt with a shovel and a wheelbarrow, you would think, wow, that's going to be a lot of work. And it is. But if we can come up with a definition of work, we can actually quantify how much work it's going to take, put a numerical value to it. And, like a big hole like this, if you can quantify how much work it would take to dig that hole, then you can start doing things like estimating fuel costs and machinery and all that sort of stuff there. So being able to quantify work seems like an important thing. Whatever our definition of work is, it should involve an effort and an accomplishment. So not only do you have to try, you actually have to succeed in doing something. So in physics, we define work. 3 little lines is our symbol for a definition. Work is defined as force times distance. The force is our effort, and the distance we move something is how much we've actually accomplished. And so we just abbreviate it W equals FD. Work equals force times distance. And if we look at the units in the metric system, we're going to measure force in newtons, and we're going to measure distance in meters. So Newton meters would be a good unit of work. If we break newtons down a little further, remember that force is the same thing as mass times acceleration. So kilograms and meters per second squared is mass times acceleration. That's force. If I multiply that by distance, well, my units become kilogram meters squared per second squared. Okay, so there's our distance. These are our fundamental units. Fundamental means you can't break it down any further. We broke newtons down into a mass and an acceleration. We broke acceleration into change in velocity over time. Okay, so, and this is also, fundamental units are also known as the MKS system. But there is also a common unit. There's one word that we use to represent the quantity of work, and that unit is joules. That's called our common unit. So fundamental is meters, kilograms, and seconds, or combinations thereof, and it can't be broken down any further. Our common unit is just one word. If we were to do that in the imperial system, we would measure force in pounds and distance in feet. Okay, and so we should say pound feet, but it does tend to flow off the tongue a little nicer if we, instead of saying, excuse me, pound feet, we say foot pounds. And a lot of times we abbreviate LBS, plural, for pounds. But what I'm saying here, excuse me, is this is the pounds of force, because sometimes pounds is used as a unit of mass. And I should say that there isn't a common unit or fundamental units that we typically use in the imperial system. So let's practice this. Here's this kid pushing against this rock with 250 newtons. And I'm asking, how much work will this kid do if they push for 3 hours? Well, a lot of times students like just taking numbers and multiplying them, so they might take that times 3, but this was the time. So the force definitely was 250 newtons, but they didn't move that rock, or we're assuming that kid can't move that rock. So even though there was force, there was no accomplishment. Even though there was an effort, there was no accomplishment. So no work was done. All right. The other thing we have to be very careful of to consider is that the force and the distance moved, the effort and the accomplishment, have to be in the same direction. So before we were just saying force times distance, but now I'm saying this is the force that is parallel to the distance. Okay, so we're just using the parallel symbol to make sure that we take the force and multiply it by the distance, but they have to be parallel. Well, let's do an example now. Let's say we have this mass here that we're going to move. It's 950 newtons of weight, and this forklift is going to move at a distance of 5 meters. How much work was done? Well, you might be tempted to say it's force times distance. You'd multiply those two numbers, but that's not true. We have to be careful. The distance it moved was to the left, and when we say this weighs 950 newtons, that's gravity pulling down with 9,500 newtons. That's gravity pulling down, but the forklift must be pushing up with 9,500 newtons. So those were perpendicular to each other, not parallel. So you could say that there was this much force, but it moved no distance, or there was no force in the direction that it moved. Either way, 0 joules of work were done. And you think, 0 joules of work, but we moved it. Well, remember when we did the elevator problem where we graphed the force on this mass over time? A little more force was needed to accelerate it in the up direction, and then a little less force was needed to decelerate it back to a stop. But the average force was 0. So if this mass here is sitting still and then we accelerate it, we have to push with more force to get it going and then less force to slow it down. But that force is not 9,500 newtons. It just depends on how fast we accelerated it to get it over there. All right, now if we take that 9,500 newton object and move it up 1.3 meters, we have done work there this time because the force and the distance were in the same direction. They were parallel to each other. So it is as easy as just taking the 9,500 times 1.3, and we get about 12,000 joules of work was done to lift that. And we were able to quantify how much work was done. Now, this is not on the forklift. We're going to tie a rope around this object and drag it along the ground. Now, if this was frictionless or on very, very, very low friction, it would take very, very little work to do that. So I'm giving you the coefficient of kinetic friction. We're assuming that it already is sliding. And we're going to slide it along here. Even though it weighs 9,500 newtons, that's not how much force the forklift was doing. Because my question is how much work is the forklift doing? Okay, so the force of friction is the coefficient of kinetic friction times the normal force. So the normal force was 9,500. The coefficient of kinetic friction was 0.97. So how much friction we're going to get is 7,500 newtons of friction. And that's opposing the motion. So if the forklift wanted to move that at a constant velocity, they would need to pull with 7,500 newtons to move it at a constant velocity. So that's how much force the forklift was applying. It applied that effort over this distance accomplishment. So 26,000 joules of work were done sliding that object from here to here. All right, now let's see if we were to graph that. If we were to graph the force multiplied by against the distance, if it was the same force all the way through like this, through the entire distance, we could calculate the work done by finding the area under that line. Because on this dimension of that rectangle was force, the base was distance, and just force times distance would give us the area, which would be work done in joules. So a little bit more back reminder about static friction versus kinetic friction. Static friction tries to hold it stationary, and friction adjusts to try to get it stationary up until some point, and then it can break free, and then it can start moving with kinetic friction. And the coefficient of kinetic friction is always going to be less than the coefficient of static friction. So if we graph what the forklift did over the distance that it did it, it's going to have to pull with more force to break it free of static friction and then actually accelerate it. Okay, and then it's going to taper off to the force of friction here. But when it slows back down to a stop, the forklift had to pull with less force to let friction slow it back down. But the area under that line would tell us the work done by the forklift. And this little area here that's excess would make up for this little area here that was missing, and it would just simply be the average force times the distance gives us the work that was done. And a little connection back here to springs and Hooke's law. Remember, if we push the spring a little bit, it pushes back with a little bit of force. But the more and more and more we push the spring, the more and more force the spring provides. So we have to provide more and more force to do that. But the total amount of work done compressing the spring to here would be the area under that line. Well, let's see if we can calculate it. It's a triangle, so it's 1/2 base times height, or 1/2 the height times the base, or just the average force times the distance. So remember, the force of a spring was the spring constant times the displacement. So the spring constant times the displacement would give us this maximum force at that displacement. Half of that would give us the average force. So that's the average force times the displacement, and that's how we would calculate how much work was done. It'd be 1/2 kx squared would give us the work done. So if this person weighs 600 newtons and they're going to run up these stairs, to calculate the work done, do you take this force times this distance, or force times this distance, or force times this distance? And there they go. It is going to be this one right up here. Here's why. Gravity is pulling down with 600. They have to be pushing themselves up with 600 newtons. So you have to measure the distance they traveled up. The force has to be parallel to the distance. Now, if that person is stopped down here and they accelerate, they have to push with more force than 600. But as they slow back down here to a stop, they have to push with less force than 600 newtons. So the average force going from stopped here to stopped there would just be what they weigh. Okay, so it would be the 1800 joules. All right, just another quick example, but if this crate weighs 2,000 newtons and the crane lifts that up a distance of 15 meters, it's really as simple as taking force times the distance, because the force was down, that's the force of gravity, but we're trying to find the force or the work that was done by the crane. So gravity's pulling down with 2,000, but the crane was pulling up with 2,000, and it moved that distance up. So 30,000 joules of work to lift that crane. We can quantify the work that we do. So here's this person pushing the lawnmower here, but they are pushing in line with their arms with 360 newtons of force at a 51-degree angle. We studied vector components, so we could find that there is a component of force down and a component of force parallel to the ground. And if they move that lawnmower along like this distance here, 4 meters, you could take this amount of force, which was the force in the same direction as the distance moved. So you could take force times the cosine of the angle to find the component, and then multiply by the distance. Or instead of taking force times the cosine of the angle times the distance, it'd be the same thing, because multiplication can be done in any order. You could take the force times the distance and then multiply by the cosine of the angle. All right, so force parallel to the distance. If the force is not parallel, you can multiply by the cosine of the angle between those two to find the component that is parallel. Okay? So when we plug our numbers in there, 360 times 4.0 times the cosine of 51, this person did 910 joules of work just moving the lawnmower from there to there. Car going around a racetrack, studying circular motion. How much work is done on the car as it goes around and round and round and round like that? Well, there was a centripetal force pushing it into a circle, and the distance it's moving was a tangential distance. Those are at right angles to each other. There was no component of the force that was in the same direction as the distance. Okay? So when something moves in a circle like that, nothing is being accomplished, because after it goes around a whole circle, it gets back to the same position. With no accomplishment, there's no work. So something moving in a circle, no work is being done on it. All right, let's say that this person's really fit. They've trained for marathons. This person is a couch potato, doesn't do a whole lot, but they both weigh 200 pounds. And they're going to race up these stairs. This guy's going to crawl up the stairs, barely making it to the top. This guy is going to sprint up just as fast as they can. And in the end, when they get to the top, who does more work? Well, you want to say the person who was very fit and did that fast, but if they're going up this thing at a constant velocity, the force is just what they weigh. Or if that person accelerated a lot for the first moment and then kept the same velocity all the way up to here and then slowed down right at the top, still the average force is just what they weigh. So the force was the same, the distance was the same, both people did the same amount of work. But that just doesn't feel right. This person did something very different than that person. So what is different? Okay, the force was the same, the distance was the same. Something was very different about the person who did that quickly. And time is the key factor that's different here. Okay? That this person did it in a very small amount of time, and this person took a lot longer time to do it. That introduces us to the idea of power. The person who raced up that was more powerful or exerted more power. So how do you think? How do you think we should define power? Is it work divided by time, or should it be work times time? Well, the person who did they did the same amount of work, but the one that did it in less time was more powerful. Okay, so we're going to divide by time, because if this number here is smaller, you're dividing into there with a smaller number, that results in a larger amount of power. So power is defined as work divided by time. And work was defined as force times distance. And now we're still dividing by time. Let's look at the units of that. We're going to do the metric units. So work is measured in joules, time is measured in seconds. So units of power could be joules per second. If we talk about work in terms of force and distance, then we could say Newton meters per second, just force, distance, and time. Now, this here is not the common unit, nor is it the fundamental unit, because we can take newtons and break them into a mass and an acceleration. So this is force, this is distance, this is time, and if we simplify that, we get kilogram meters squared per second cubed. And that is the MKS unit of power. It's also known as the fundamental. Can't break it down any further because we were able to break newtons down. The common unit, the one-word unit for power is watts. Okay, so we're going to be measuring power in watts. If I were to do that in imperial units, we would measure the distance in feet, the force in pounds, and the time in seconds. So foot pounds per second would be our unit of power in the imperial system. And again, we don't do fundamental or common units. It's just not done. Thomas Newcomen was the person who invented the steam engine. But James Watt is the one who made some very big improvements with the valves and being able to get force on both sides of the valve as it went. So he's accredited in greatly improving the efficiency of the steam engine. And for his steam engine, as a marketing scheme, he came up with this idea to be able to communicate to people how good his machine was, and that's by comparing his machine to literally a horse. And that's where we come up with the term horsepower. And James Watt studied horses that were working in a mill to grind wheat or flour into flour, and he found that your average horse could provide 33,000 foot-pounds per minute. So he calculated that it was 180 pounds of force that the horse was providing through some distance over a period of time. Okay, 33,000 foot-pounds per minute. And if I divide that by 60 to get minutes into seconds, that's the same thing as 55.0. I missed a decimal there. I'm sorry, I did say that wrong. It is 550 foot-pounds per second. 550 foot-pounds per second is the same thing as what one horse can do. And I should say that it's what one horse could do for a 4-hour shift working the mill. So 550 foot-pounds per second is the same thing as 1 horsepower. So let's take this horse and let's say that as the horse pulls the plow through the ground, there's 180 pounds of resistive force on the plow. So the horse has to pull with 180 pounds to move the plow at a constant velocity. And my question is, well, what's that velocity? So you take the definition of power, which is force times distance divided by time, and do you see anything in that equation that talks about velocity? Well, how about that little piece right there? Distance divided by time. So another way of calculating power would be force times velocity. So if your average horse could do a power of 550 foot-pounds per second, and this was the force, what's the velocity? Well, we're going to divide both sides by 180, and that horse could walk forward at about 3.1 feet per second. All right, now let's say which of these examples uses more power. And that would be lifting 550 pounds a distance of 1 foot in 1 second. So 550 pounds, 1 foot in 1 second. Or lifting half as much force, twice as much distance in the same amount of time. So this number is half as much, this number is twice as much, and, well, it's going to be the same thing. It's going to be 1 horsepower. Well, what about lifting half as much force again, the same amount of distance, but doing it in half as much time? So half as much force and half as much time, well, that's also going to be 1 horsepower. Can a person put out about a horsepower? Yes, they can. If a person who weighs about 137 pounds lifts their weight 2 feet up in about half of a second, yeah, a person can put out about a horsepower. In fact, a horse can put out a whole lot more than a horsepower, but only for short periods of time. Okay, a horsepower is defined as what it can do over the course of 4 hours. So let's compare imperial units to metric units. 1 horsepower is 550 foot-pounds per second. 1 watt is lifting 1 newton, 1 meter in 1 second. So how many horsepower, or 1 horsepower is how many watts? We got to convert feet into meters. We got to convert pounds of force into newtons, and seconds are already done for us. So let's start with 550 foot-pounds per second. We're going to multiply by a whole series of fancy ones. 12 inches is the same thing as 1 foot. That's a fancy one. But feet on top and feet on bottom cancel. Remember, I'm trying to get feet into meters. Let's get inches into centimeters. That's a fancy one. Inches cancel. And then we can get centimeters into meters. That 100 centimeters is 1 meter. Centimeters on top, centimeters on bottom, cancel. My unit just became meters. Now I don't have to start a new problem. I've got seconds way over here. I've got pounds of force way over here. I can cancel it if I have something with pounds of force in the denominator way over here. 1 kilogram is the same thing as 2.20 pounds. So pounds up here, pounds down there, cancel. And then I'm still trying to get pounds into newtons. I just got pounds into kilograms. So let's get kilograms into newtons. 9.8 newtons, same thing as a kilogram. So let's see, kilograms here and kilograms there cancel. My unit becomes newton meters per second. So I just have to take that, times that, times that, times that, times that, times that, divide by this, divide by that, divide by that, and that's what we get. So 746 newton meters per second is the same thing as 746 watts, and 746 watts is the same thing as 1 horsepower. You can calculate your horsepower. In fact, I would encourage you to do that, but you just have to know what you weigh. So let's say this person's running up the hill like this, pushing with an average force of 700 newtons, a distance of 6 meters, and a time of 8 seconds. How much work did they do? Well, it's just force times distance. They did 4,200 joules. How much power did they exert? Work divided by time. This much force this much work divided by that much time. 525 watts is how much power they exerted. And we can convert watts into horsepower because 746 watts is 1 horsepower. So that divided by this, about 0.7 horsepower, which is pretty good for that length of time. So let's say that we're going to design an elevator to be able to lift the elevator up the Empire State Building and do it in 60 seconds. So we want the elevator capacity to be 6,000 pounds. The elevator itself is 1,500 pounds. So we've got to be able to lift 7,500 pounds, 1,250 feet in a time of 60 seconds. So what size of motor do we need to do that? Well, this is the force, that's the distance, that's the time. So we need a 156,000 horsepower engine, right? And be careful, that's not horsepower. 156,000 foot-pounds per second is what we need, but 550 foot-pounds per second is what a horsepower is. So we're going to cancel those units and we get about 284 horsepower. So that's a little bit about work and power. Make sure the force and the distance are in the same direction. If they're not, find a component that is. And then if we take work divided by time, we get power. 550 foot-pounds per second is 1 horsepower, or 746 watts is also 1 horsepower.